This is NASA TV.
There have been hundreds of science experiments and technology research projects on board the International Space Station since the first modules of that station were launched 15 years ago. The research has covered things like human life sciences in order to find out how being in that environment impacts people and to find out ways to mitigate the negative effects of that, as well as research in biology and physical sciences and astronomical sciences and technology development and research to support future human exploration beyond low Earth orbit. And much of this has been done with an eye toward how what we've learned in space can be applied to help people here on Earth. For a recent international conference, the International Space Station Chief Scientist, Dr. Julie Robinson, was asked to put together a list of the top 10 research results from the space station. And she joins us today to talk about some of those. Julie, give us a brief reminder of the criteria that you used when you thought about all that's been done on board the station in these years to try to decide which were the top 10 results.
Sure. You know, I have this great list in my head, at least, of all the wonderful things that the space station has accomplished. And I set aside all the engineering achievements. I set aside all the advancements in international relations and how we work with other countries in space. Set that aside. I set aside all the spin-offs where a new technology has led to life-saving devices on Earth. And I just focused on the research results from the research that we've been doing over the last 15 years. I looked at those results for examples where either it was, a significant scientific publication in a major journal, or where it had a very direct connection right back to people's lives on Earth, and I really drew from those. I also used inputs from some of my colleagues, but of course the list was painful to develop because there are many more than 10 outstanding research results that have come from the space station. But I was forced to limit myself to 10, so I did.
And there are more, but we'll talk about those 10 here. And a lot of times when we talk about the science and research on board the station, we have a tendency to think about the things that we see astronauts and cosmonauts working on. But I want you to repeat something that I've heard you talk about before, and that's that we do a disservice to the overall thing if we neglect all of some of the things that go on that really don't have human crew member involvement.
Right. We actually design experiments to have as little crew involvement as needed so we can do as many things at one time as we possibly can. A great example of that is the alpha magnetic spectrometer. It takes literally no crew time. Maybe once a year they reboot the computer. But it has collected over 20 billion observations of galactic cosmic rays since it went up in 2011. And it had significant papers that came out this year. The most significant papers from that experiment are definitely yet to come. And so even when the crew's asleep, there's a huge amount of science data coming down.
Well, it's not, of course, to say that the human crew doesn't play a role. And number 5 on the top 10 list is just one example of that. Number 5 is pathway for bacterial pathogens to become virulent. This was a result that was supported by the crew members, but I believe the investigation actually grew out of a concern for the health of a crew in space.
That's right. When we've done some studies of crew members' health, one of the things we found is crew members' immune function is disrupted. So we would actually expect them to get sick more often than they do. They're also incredibly healthy people, and so that may be part of why they don't. And there was some ground-based data that suggested some kinds of bacteria might be more able to grow in space. So originally, our human research program funded a study of salmonella bacteria in space. Those are bacteria that cause foodborne illness. A lot of people around the country have had salmonella. It kills people all around the world who get that foodborne illness, and if you don't have access to hospital care and get a severe case, people can definitely die of salmonella food poisoning. And so originally it was funded by NASA's Human Research Program because they were worried about if a few salmonella got into the food supply, say on a mission to Mars, it could become a life-threatening event and you could lose, it becomes a risk to losing the mission. So they funded a study to test the bacterial growth of salmonella in space, and echoing the ground analog studies that had been done ahead of time, when those bacteria were grown in space, brought back home, and infected an animal model, they were much more pathogenic. They were much more able to cause illness. And so that was a really significant result. It was published in the Proceedings of the National Academy of Sciences. And what was most important about it scientifically was not just that they became more able to cause illness, it was that the scientists were able to determine the genes that had turned on to cause that to happen. So it was a new genetic pathway for causing illness that had not been identified before.
That the bacteria became even stronger or more capable of causing illness in that environment than they would have been on Earth.
Right, right. And by understanding that pathway, that opens up the knowledge to go in and intervene. So that opens up the possibility of either figuring out some kind of treatment that if somebody has salmonella could help them get better quicker, or even potentially finding a way to have a vaccine where somebody could be inoculated and be more resistant to salmonella. So those early results were quite compelling. They had to be followed up, so they were repeated in a follow-on study. Scientists started changing the media that they were growing in to see if they could show that that pathway was really important, and those results came back significant and were published. So then the research teams kind of split up into a number of different groups who have been looking at ways to advance that further. So there's one team at the Arizona State University Biodesign Institute, and they're looking at ways to take that knowledge and transfer it to the development of other kinds of vaccines. So for example, that university has a vaccine in development for pneumonia, and they're interested in seeing if they can use a combination of salmonella and the pneumonia together to find a vaccine that might be more effective. Might help especially older people who don't respond really well to the current pneumonia vaccines. A separate team, which was a commercially funded team called Astrogenetics, flew a number of additional on-orbit studies. They tried flying a small roundworm called C. elegans. It's often used as a model for higher organisms to see, and it gets infected by salmonella as well. So they tried flying that model to really understand the mechanism, see if they could hone in on a vaccine. And right now, all of that future work hasn't come to fruition yet. Science takes some time. But the reason I called out this result, first of all, is because it was such a significant advancement in its own right, in terms of that you would study bacteria in space and that you could really learn something novel about bacteria by studying them in space. And it's definitely, that knowledge is now tumbling around in the scientific community, and people are seeking the different ways to take that and leverage it to make something that's really good for improving health on Earth. And now, just recently, there have been additional work that's been started to see about taking that knowledge and really turning it into a vaccine by a university that's very good at developing vaccines and has done that in the past. So it takes time, but I think just watching the development of this case over the last few years has been really great.
The next result on our list includes one of the biggest numbers that's associated with anything here. Number 4 on the list is 43 million students and counting. You're counting, figuring 43 million students have been involved in some way with space station educational endeavors. And I'd like to get you to try to flesh that out. Start with some examples of students who have actually had their own experiments fly in space.
That's right. Google YouTube had a contest where students from all around the world proposed what experiment they would do in the space station. It was a huge contest. They had to post YouTube videos of what they would like to do and why. And then the 2 winners of that contest both had their experiments carried out by the astronauts last year. One of them will be publishing those results in a scientific journal. It's really amazing to see what students can do when they're offered access to such an innovative platform.
Are there other similar projects where kids are flying their own experiments?
Another area which is amazing is through the NanoRacks system. Students are able to fly basically small contained packages and send those up to the space station. There are schools that actually raise the money every year for their science fair projects to go to the space station. We don't pay them to do that at NASA, but the schools through NanoRacks and through CASIS, the Center for the Advancement of Science in Space, can actually take advantage of that opportunity to use ISS.
And to step there for just a moment, CASIS is an organization that's designed to help not just students, but a lot of other people outside of NASA take advantage of this laboratory.
Right. CASIS works with other government agencies like NIH or NOAA or the National Science Foundation. They also work with the private sector, commercial companies, pharma, industrial companies, materials companies, and then also education organizations and nonprofits to help the taxpayer, all of us, get absolutely everything we can out of the space station to facilitate all those groups having access and to do innovative things.
In terms of the way the station's touching students, there are other ways that students are involved without flying their own experiments as such. What are some of the other projects or experiments that they're involved in?
Yeah, we've had about 1.7 million students that have done something we call inquiry-based learning. And that means the students were looking at or learning about an experiment that was going on the space station and doing a parallel experiment in their classroom on the ground. They were developing their own hypotheses, testing what would happen, and really doing real science. And that's been shown, inquiry-based learning has been shown to be one of the most fundamental things that changes a student's interest in math and science, because they really start asking their own questions, not just memorizing terms or looking at equations, but really asking questions and answering them. So that's incredibly influential in our nation to have that many students involved in space experiments. Then the other millions of students that I talked about, to make that 43 million, those students have mostly participated in a variety of other investigations or other activities where they could watch astronauts, videos of astronauts demonstrating things, showing Newton's laws of motion, for example. There are great videos and curriculums out there using those different tools. Teachers use those in their classrooms, just grab them and show a little bite, really encourage the students. They'll hear it from an astronaut in a little different way than they hear it from their regular teacher.
And there's a lot of different kinds of experiments that over the years station crew members have participated in to do that. Sometimes they even get a chance to talk directly to students.
That's right. Students talk to astronauts in two ways. One is there's a whole ham radio organization that volunteers, the ARIS organization. They volunteer to connect the astronauts and do the connections on the ground so that the astronauts who are sort of in the evenings on the space station after their workday is over, if they want to make a contact, they can talk to a classroom back on Earth, and the classrooms get prepared and ask questions about the science that they're doing, ask questions about what it's like to live and work in space. Another thing we have are education downlinks, where schools can be set up within a school assembly. The astronaut comes on the television loop, the students can ask questions, they'll have contests at the school to decide which are the good questions, and students get to ask them, the astronaut answers them. They're really great opportunities for students to learn about space and to really understand how important a part of our future it really is.
And there are, I know particularly some other things like the spheres experiments or the EarthCam investigation, where there are millions of people who've been involved in some way.
Oh yeah, and Sally Ride EarthCam is one of the longest running education activities we've had on the space station. Middle school students control a camera that's mounted in the window. They learn about the Earth. They develop the files to tell the camera when to take pictures. Students at UC San Diego run a little mission control center to put those together and control the camera on the space station. And we actually have a flight controller in mission control today who was an EarthCam student early in her career. So these are really influential activities.
Our next result on the list is something that I always think of as kind of a science fiction-y characteristic to it. Number 3, dark matter is still out there. Because it wasn't that long ago that dark matter was something in science fiction. As you've described it in the blog, give me the non-astrophysicist version of what we're talking about. What is dark matter? Yeah,
so I'm definitely not an astrophysicist, so I have a genuine biologist viewpoint of astrophysics.
You give it the journalist viewpoint, which is even simpler.
So, you know, basically, if you do all the math and you add up everything in the universe, there's a whole bunch of mass out there we can't see. And there are different theories for what that might be, but the best theory is a theory of dark matter, that there's a bunch of matter that is not reflecting or glowing in any way, and so we just can't see it. It's not, whereas we can see stars, those are evidence of matter out there. So that requires a set of theoretical processes that haven't really been measured. And one of the things that boils out of that theory is if there was dark matter that makes sense to the physics we know today, those particles every now and then should bump into each other and annihilate each other, and that would produce positrons. So positrons are little positive particles. You can think about them as
That's
that.
evidence of this collision, which is evidence of their existence.
Right, right. Now there's some other things that produce positrons out there that we understand, astronomical sources that we can measure and we understand. And so what physicists have been focusing on to understand whether dark matter is out there is looking at the positrons they can measure that are coming from the universe all around. So the alpha magnetic spectrometer is the most sophisticated tool we've ever had for measuring the galactic cosmic rays, including positrons that I talked about. And as I mentioned, they've had over 20 billion observations now. That's a lot of data to sift through. They published in the early spring, they published their first publication in Physical Review Letters, and in that they looked just at the positron data that they had, not at all the other particles. And they looked only at the energies from 0 to 300 giga-electron volts. Now the instrument goes from 300 to 1,000 giga-electron volts, or 1 tera-electron volt. That data is rarer. Those are higher energy particles, so that's still data to come. But up to 300, that's the data that other instruments have occasionally been able to measure, instruments like Pamela and Fermi. Okay. So what AMS did, because it's got so much statistical power from getting all these observations, is when they publish their data, it's the best data that science has ever had on how many positrons there are in the universe and where they're coming from and what their energies are. And
it's getting all this data because it's up on the space station, it's there all the time.
Right, right. This is an enormous magnet. The magnet is, essentially the size of a small house. And so this enormous magnet up there is collecting these, measuring the direction they're coming, measuring their masses, measuring their energies. And what Nobel laureate Dr. Sam Ting and his team of over 350 collaborators were able to publish early in the year is basically they showed that with all of this data, there are way too many positrons in the universe, that they're not explained by all those other processes that are well known in astronomy. There are a lot of high energy positrons that just aren't explained by any other phenomenon. So the careful astrophysicists, they're not going to say that's evidence of dark matter, because you can't prove something by just measuring there's too much of something.
But it must be something.
But it means there's something there, and that something is not explained by all the other theories. It's not explained by looking at pulsars and looking at all the other processes that we see going on in the universe. So it's support for all of the theories about what dark matter and dark energy are.
Yeah, it's coming from somewhere.
Right.
Something has caused it. And this is a great example of the International Space Station as a science platform. There are other things similar to the AMS that are using the station as a place to be in order to gather this information.
Right. Professor Ting put the AMS on the space station just because we have these amazing solar arrays, all this power, all this data. It would have required building an enormous satellite, much bigger than satellites we ever build for astronomy, in order to support this large magnet. And the space station was the perfect place to do it.
And there are other investigations that are taking advantage of the same perch.
Yeah, we'll have another astrophysics payload going up called CREAM, looking at other aspects of cosmic rays. And of course the Earth science instruments, there are dozens of those either going up soon or being planned. It's really becoming a key platform for both looking at space and looking down at Earth.
Next on the list is something that's grown out of one of the biggest machines on the space station. Number 2 is robotic assist for brain surgery. In this case, the result is thanks to a lot of work that was on the ground to create a spin-off from critical station hardware that was developed by one of the station's international partners.
That's right, and I said I didn't include spin-offs, so I have to tell you why I did include this one, and that's because it's not like you could just take the technology from the space station and use it on people's brains. It took a lot of research in between there. It took a lot of science in between there to get it. It was not a direct spin-off from the space station. But the Canadarm and the Dexter, which is the the fingers, essentially, of the Canadarm were developed by the Canadian Space Agency. It's their major contribution to ISS, and our Canadian colleagues have extraordinary capabilities in robotics. The MDA, the company that designed that for the space station, in space hardening and developing reliability that was suitable for doing things like assembling a space station or carrying an astronaut in space. Once you do that, you have really pushed your technology in robotics. And you've also had to have technology that was resistant to radiation, that was resistant to that harsh environment of space. So what they wound up with, once they miniaturized it, was a robotic arm that could be used inside an MRI machine successfully in that magnetic field. And now it's, of course, very small, and it can be controlled by a neurosurgeon, and it's more stable than the human hand can ever be. And that's enabled neurosurgeries and some surgeries on patients where there was no surgeon who could try to do the surgery to remove a tumor or to remove other problems. And they just published in a scientific journal just 2 months ago, the results of their first 35 patients, the patient outcomes, where they've actually followed them now that they've recovered from the surgery. Those are reports about people who are alive today because of the space station.
And this is a thing called NeuroArm.
Right, it's called the NeuroArm.
Can you give me the quick version of how this helps a surgeon? I mean, is this a thing that they hold that has a scalpel on it?
So essentially the robotic mechanism, they control it with some triggers and some controls here, and they're able to, they do what they need to with their hands, and then they're able to come in and just excise a little tumor while the MRI is on so that they can get the position just exact. And that's how it works.
And it's the fineness of its ability to keep in one place that's important, because when you're working in the brain, there are areas you don't want to go. Right.
It's that fineness of control, and then being able to do it in the MRI so you have the image to help you get just that one precise place.
Because anybody who's had an MRI knows about how you have to make sure you don't even have anything metal on you as the patient.
Right.
And now they're talking about taking the whole instrument inside that environment.
Right.
It's not exactly directly a doctor's arm, but it is something that they control.
That they're controlling, right.
And it's saving lives in surgery.
That's right.
And it's also leading to some other research too, right?
Well, so you get this feedback then whenever you develop a new technology, you bring it back to the ground, then you can bring those technologies back into space. So there's a back and forth as we make those technology advancements, and that's definitely what's going on with robotics.
That's leading to those other things. Benefits on Earth is something that we always like to talk about, and that's certainly one of them. The benefit on Earth that's associated with the final item on the list is pretty apparent. The #1 result from the International Space Station research is new targeted methods of chemotherapy drug delivery with clinical breast cancer trials now in development. Is that all? Are you just changing the way we treat cancer?
Well, cancer is not a thing, so we cannot cure it, and nobody can cure it on Earth, and nobody can cure it in space. But what we can do is take biomedical advancements and find ways to use that special environment of space to advance our knowledge and find an application that can really help patients on Earth. And so the way that this worked very early in ISS, back in Expedition 5, we had an experiment called MEPS, microencapsulation of particles in space. And the basic idea was that if you could make the right kind of little balloon, and this is almost at that nanoscale we were talking about in the beginning, if you could make the right kind of little balloon, then you could put a cancer treatment drug inside of that, and it would target, based on the properties of the balloon, it would sort of target the target tissues. For example,
to carry the drug to
the tumor, for example. And folks work on that because cancer treatment drugs have so many horrible side effects, and they have their side effects when they're hitting organs that don't have cancer. And so you want to find things about those microballoons that will have them tend to want to go based on their molecular attraction, or based on the physiology, or based on a variety of things. You want them to kind of go where the tumor is and not go other places. So scientists thought that if you took convection, that mixing that I talked about before, out of the equation, that you might be able to get those little microballoons to self-assemble in space, and that those microballoons would have a set of properties that nobody had been able to make on Earth. So the scientists proved that they could do it in space. Right after that, the Columbia accident happened, but they had their results, and they couldn't fly in space again right away. So they came home and they sharpened their pencils. They spent 5 years developing a piece of equipment that could mimic space enough to make those same microballoons on Earth.
So in order to manufacture it here instead of there.
Right, because you want to be able to make those in clinically relevant quantities in nice, clean, aseptic environments. So you have something you're really willing to inject into patients. And so once that was approved, now they've been refining techniques for how they would use that microencapsulation technology, both to target tumors that are scheduled for ablation, so that the ablation technologies only affect the tumor and affect the surrounding tissues less, and also to deliver chemotherapy treatments. Now, in some rodent models, they had real effectiveness in treating tumors, sometimes 14 times more effective than the chemotherapy drug alone. But they have not yet made it to human clinical trials. They just received some funding to do the next stage of development so that they would be ready to start clinical trials very soon. And they already have the protocols in place that they could even do those at MD Anderson Cancer Center. But these things just take a little bit of time. And one of the reasons I put them on my top 10 list, I hadn't been talking about them for a while, but they moved on. I talked about them for a while when they got the patent, and I thought, oh, here comes the FDA trials, and then nothing happened and nothing happened. Because at each stage of this process, scientists have to raise money, they have to find the support, they have to answer the questions of regulators. And that's why I picked them as #1, because just that determination that these investigators have had to keep taking that knowledge that came from space and overcoming each barrier. When they couldn't keep flying to space, they figured out how to make it on the ground. When they figured out how to make it on the ground, now they're figuring out how to answer all the regulators' questions and then keep moving that forward. It takes real dedication to take our space results and make them save lives, and it's amazing. It's going to be amazing if this one pays off. These are great. Is there anything that's going on the station now that has potential to be on next year's list? Well, you know, if I'd done the list on a different day, I might have picked other things. Yeah, I didn't talk about some of our great spin-offs. For example, you know, right after the horrible hurricane in the Philippines, the water treatment system that we developed for the space station has been deployed over the last 10 years now all over the world because it really works in disaster regions, and that's saved thousands of lives, prevented lots of cholera, and it was deployed right out to the Philippines right after the hurricane came through. Also, you know, women in rural areas around the world, from the far Arctic to Brazil and Kenya, are having the opportunity to have the ultrasound technology that we developed for astronauts to be used to help them screen pregnancies so they can get to a hospital before they go into labor and have a complication, and that's credited with saving thousands of lives. There's a nonprofit organization now that is doing nothing but testing how to spread that technology around the world, working with the World Health Organization. These are all very exciting. Thank you for helping us understand it better. Julie Robinson is the International Space Station's chief scientist, and you can read Julie's blog, A Lab Aloft, online at blogs.nasa.gov. You can also follow along on Twitter at ISS_research and on Facebook at facebook.com/ISS. You can also see the station as it's orbiting above the Earth. When it passes above your location, you can find out where that is by checking out our site, spotthestation.nasa.gov. I'll remind you, too, that you can keep up with the mission on board the International Space Station daily here on NASA TV and online at nasa.gov by watching our Space Station Live program weekdays at 10 a.m. Central Time. And you can catch up on the week's activities every Friday by checking out nasa.gov for our Space to Ground web feature.